A 200-meter water drop inside a sealed concrete shaft can generate enough electricity to power a city for a few seconds. The same basic idea, falling water under pressure, is what makes hydropower work. Offshore oil platforms use a different kind of industrial physics, but the same principle applies. A large, tightly controlled system turns a natural force into usable energy. In the North Sea and other offshore basins, a platform can sit in water hundreds of meters deep and produce thousands of barrels of oil every day while housing a crew of 200 people. No road reaches it. The nearest hospital may be a helicopter ride away. Food, water, medical supplies, spare parts, and people all arrive by ship or air. And yet the facility runs around the clock in some of the roughest weather on Earth. An offshore platform is not one thing. It is a stack of systems. At the bottom are steel jacket legs driven deep into the seabed. On top sits the main deck, which can weigh tens of thousands of tons before equipment is installed. Above and around that are modular process units built onshore and lifted into place by cranes. Each module does a different job: power generation, drilling, separation, processing, and accommodation. The industry grew because the easiest oil was not enough. Onshore fields were tapped first, then shallow coastal waters, and finally the deeper basins where the geology was promising, but the sea made everything harder. Once drilling technology improved enough to go farther and deeper, offshore production became one of the major ways the world found new barrels without opening entirely new land sites. The platform became the answer to a simple economic question: if the oil is underwater, can we still reach it profitably? Below the platform, the wellheads connect to wells that can extend several kilometers into the rock, sometimes vertically and sometimes at a sharp angle to reach a reservoir horizontally. Modern directional drilling lets one platform tap a wide underground area without moving the rig. Sensors at the drill head send data back to the surface in real time, and engineers steer the bit the way a surgeon guides an instrument, except the tool is kilometers below the sea. That reach matters because offshore fields are rarely simple stacks of vertical wells. Reservoirs can be thin, fractured, or spread out over a broad area. Horizontal drilling increases contact with the reservoir and makes it possible to drain more oil from a single platform location. In effect, the platform is a fixed base camp for an entire subsurface map. When oil and gas reach the surface, they arrive as a pressurized mixture of crude oil, natural gas, salt water, and sand. The first task is separation. A three-stage separator system uses gravity, pressure changes, and heat to split the stream into gas, oil, and produced water. The oil goes to storage or export. The gas is exported, re-injected, or burned on the flare. The water is cleaned before discharge. That water becomes a major issue as a field matures. A North Sea reservoir that once produced mostly oil may later produce several barrels of water for every barrel of oil. The water carries traces of oil and dissolved chemicals, so it must be treated before it can go overboard. Hydrocyclones use centrifugal force to spin out oil droplets, and flotation units use fine bubbles to lift the remaining traces. North Sea rules require discharged water to stay below very low oil content limits, so operators test it constantly. Produced water is not just a disposal problem. It is also a sign of how a reservoir is aging. As pressure drops and water cut rises, the economics shift. A field that once made easy oil becomes a field where operators spend more and more effort separating a dwindling hydrocarbon stream from a much larger water stream. That changing ratio drives many decisions about how long a platform should remain in service. Power on the platform usually comes from gas turbines, which are essentially jet engines bolted to generators. Most platforms run multiple turbines in parallel, so one can be kept in standby. The turbines power drilling motors, compressors, separation equipment, lighting, heating, and controls. A large platform can consume tens of megawatts continuously, about the output of a small municipal power plant. Waste heat is recovered and used to improve process efficiency. The structure itself is another feat of engineering. Fixed platforms use steel jackets, lattice frameworks welded into three-dimensional structures and anchored deep into the seabed. They are designed to flex slightly under wave loading rather than resist it rigidly. Engineers calculate fatigue life for every joint because waves cycle the structure millions of times over its service life. Divers and remotely operated vehicles inspect cracks, corrosion, and marine growth on a schedule. Inspection never really stops offshore. ROVs scan welds, sonar maps scour around the legs, and thickness measurements track how quickly corrosion eats into steel. A platform that looks solid from a distance may be managing a long list of hidden maintenance problems under the waterline. That is why operators spend so much time planning work windows, because every inspection result feeds directly into the next maintenance schedule. Those inspections are not optional. Every wave, storm, and temperature swing puts stress into the same welds and braces. Over time, tiny cracks can grow, so the jacket is treated like a giant fatigue machine that must be watched continuously. Offshore engineering is partly about strength, but it is just as much about knowing how metal behaves after years of repeated loading. In water deeper than about 300 meters, a fixed jacket becomes impractical. Floating production systems solve that problem. Semi-submersibles sit on pontoons below the wave zone and are held by spread moorings. They move a little with wind and current but remain centered over the wells. For very deep water, floating production, storage, and offloading vessels, or FPSOs, are used instead. These are ships converted into production plants. They process oil on deck, store it in hull tanks, and offload it to shuttle tankers every few weeks. FPSOs changed offshore economics because they made remote development possible without building a permanent export pipeline to shore. That flexibility opened fields that would otherwise have been too expensive to exploit. A floating plant can move when a field is exhausted, and that mobility is one reason the concept spread so quickly in deep water basins. Drilling takes place at one end of the platform. The drill floor sits above the main deck, and the drill string hangs from a top drive that rotates it from above. Drilling mud is pumped down the pipe, cools the bit, lifts cuttings back to the surface, and returns through the annulus. The mud is carefully engineered to balance formation pressure. Too light and the well can kick. Too heavy and it fractures the rock or loses fluid into the formation. The mud system is its own piece of chemistry and hydraulics. Operators tune density, viscosity, and additives so the column stabilizes the borehole while still allowing cuttings to surface. In offshore drilling, that mud is one of the main defenses against instability underground. It is both lubricant and pressure control medium, and it has to behave correctly under heat, depth, and changing formation conditions. A well control event is the industry's most serious drilling hazard. If formation pressure overwhelms the mud column, fluid can surge up the wellbore. The main defense is the blowout preventer, a massive valve assembly that can close around the drill pipe or shear through it in an emergency. Drillers train for kicks constantly because a blowout is the nightmare scenario for any offshore well. Once a well is drilled and cased, it is completed for production. Engineers perforate the casing at the reservoir zone, create flow paths, and often stimulate the rock with hydraulic fracturing. Production tubing is then run inside the casing and sealed with a packer. When the master valve opens, the oil and gas flow up through chokes that control rate and pressure. Completion work is where the platform's long-term economics start to show. A well can produce for years, but only if the completion is designed to control sand, manage water, and maintain enough flow to justify its operating costs. The wrong completion can shorten a well's life even when the reservoir still has oil left to give. Every part of the platform is instrumented. Pressure transmitters, flow meters, temperature sensors, level gauges, and thousands of other data points feed a central control room. That control room is the platform's brain. Operators watch dozens of screens that show real-time process diagrams and alarms. Experienced operators know which readings drift on a cold morning and which values should not be trusted even when they look normal. The control system is layered for safety. A distributed control system monitors normal operation. Above it sits an emergency shutdown system that closes valves and isolates sections of the plant if critical limits are breached. If the situation worsens, a full platform shutdown can isolate the entire facility. These layers are tested on schedule because the system must work even when everything else fails. Utilities are just as important as the process equipment. Platforms make their own fresh water through desalination, usually reverse osmosis. They use compressed air for tools and instrument valves, hydraulic systems for cranes and large valves, and chemical injection for scale inhibition, corrosion inhibition, and anti-foam. The platform is a self-contained industrial city. The export system moves the product to shore. On many platforms, subsea pipelines carry oil and gas back to land or to a hub platform. Export pumps push oil into the line at high pressure. Gas may travel in a separate line or be compressed and sent with the oil. Getting the pressure right matters because too little stalls the flow and too much risks damaging downstream systems. Pipeline ties can shape an entire field's life. If a pipeline is available, a discovery may become commercially viable. If not, the project may need an FPSO or may never proceed. That is why offshore development is as much logistics planning as it is drilling. The flow path from reservoir to market can decide whether the barrel is worth producing at all. Maintenance is constant and largely invisible. Offshore teams cannot call a repair company. They have to handle everything themselves. A planned maintenance system schedules routine jobs, and technicians carry out predictive maintenance using vibration analysis, thermal imaging, and ultrasonic thickness testing. If a pipe wall thins too much from corrosion, it gets replaced. Corrosion is one of the platform's oldest enemies. Seawater, hydrogen sulfide, carbon dioxide, and chemical exposure all attack steel. Above the waterline, coatings protect the structure. Below it, sacrificial anodes made of zinc or aluminum corrode instead of the jacket's steel. Divers inspect them and replace them when they are depleted. A cheap metal is sacrificed to protect an expensive one. Weather changes everything. A North Sea storm can bring waves above 20 meters and wind gusts that shut down crane operations and helicopter flights. The platform is designed for extreme storms, but crews still feel every blast of wind and spray. Supply vessels with dynamic positioning systems arrive 1 or 2 times a week when conditions allow. Their cargo is lifted by crane nets and baskets, which can rise and fall meters in a single second as the ship rides the swell. The North Sea became such a proving ground because it combines severe weather with high operational value. Any design that survives there acquires a reputation that carries into other basins. The equipment, operating procedures, and maintenance culture developed in harsh northern waters often become the template for more temperate offshore fields elsewhere. The accommodation block keeps the crew functional. Cabins are small, but private. There is a galley, a gym, a recreation room, internet access, and a medic with equipment closer to a small hospital than a first aid kit. Because evacuation can take time, the medic handles everything from cardiac events to fractures and chemical burns until a helicopter can arrive. Offshore workers live in a highly controlled environment because safety depends on it. Rotations shape life offshore. 2 weeks on and 2 weeks off is common, though schedules vary by region and company. That pattern gives workers long blocks of concentrated work, followed by time ashore, but it also creates a culture where crews must trust one another quickly. A person stepping onto the platform needs to know that the person on the next shift left accurate notes. Fire and gas detection systems cover the entire installation. Sensors detect leaks, alarms trigger ventilation and isolation, and deluge systems flood affected areas with water or foam. The platform's fire team is trained to respond before shore-based help can arrive. The most serious incidents in offshore history have always involved multiple layers of defense failing in sequence. Because hydrocarbons are always present, the safety culture is intensely procedural. Permits to work, lockout-tagout systems, gas testing, and isolation checks are part of everyday life. The platform is full of things that can ignite, and so the organization must treat routine tasks as if they carry hidden consequences. That discipline is one reason offshore production can continue safely for decades. The platform also has to deal with the long-term consequences of production. Reservoirs produce more and more water as they mature, and the eventual amount of oil declines. Some fields become mostly water with only a small oil stream left. At that point, operators either keep producing, reconfigure the system, or plan for decommissioning. Decommissioning is an enormous task. In the North Sea, the default expectation is full removal, topsides, jacket, and subsea infrastructure. Heavy lift vessels remove the topsides, the jacket is cut up or lifted in sections, pipelines are flushed and abandoned, and wells are cemented shut at multiple depths so they can never leak. A single major platform can take a decade to dismantle and cost over $1 billion. The logistics of that removal can rival the original construction project. Specialized vessels, permits, waste handling, metal recycling, seabed surveys, and long-term environmental monitoring all have to be coordinated. A platform leaves behind not only steel, but also paperwork, liability, and a set of decisions about what can safely stay in place and what must be taken away.